Welcome to today's lesson. In this first tutorial, we will be able to graph exponential functions, and we will state all the information about our exponential functions. We are in a new chapter. Our chapter is Chapter 4, Section 4.3, Exponential Functions. So we're talking about exponential functions. So let me give you the basic exponential function. F of x is equal to a to the x. This is our first function where we're looking where the variable is in the exponent. Okay, so this is our basic exponential function. Now, there's a couple restrictions on the base. Our base, first of all, has to be a positive number. So a is going to be greater than 0. We're not going to be looking at bases that are equal to negatives. One positive number that a cannot be equal to is 1. And if you think about it, that makes sense. If our base were 1, then our function would basically just be a straight horizontal line. So that's no good. So a can be any positive number except for 1. And x can be any real number. So x is going to be an element of the real numbers. That's what this symbol means, this little E looking thing. X is an element of the real numbers. It's a part of the real numbers. It's a piece of the real numbers. It is a real number. So those are our little restrictions, but that is what we're going to be dealing with for the next few chapters. For the next few sections. So since we're talking about real number exponents, let's look at this first one just to make sure you know how to plug this into the calculator. 2 raised to the pi power. You go ahead and take out your calculator, and what we're going to need to do is use the caret button. The caret button is over there by the arrows. That will raise to any power that we want to. And in this case, when we're raising to the pi power, pi is, you have to press the second button and then the caret. Pi is hiding right above the little caret button. So when you plug that into your calculator, I'm going to give as many decimal places as I can. It's approximately 8.824977827. I think that's all that my calculator gives. Of course, this goes on forever. So you should be able to raise to any exponent that you want using the caret button on this TI calculator. Okay, what we're going to look at first is our graphs. Now I'd like to graph two of our functions, 2 to the x and 4 to the x, on one graph patch, and then we'll look at the reciprocals, 1/2 to the x and 1/4 to the x. If you have a couple different colors, that might be helpful. I'm going to graph f of x in the red color. So ultimately what I can do is plug in anything I want for x, and that's what I'm going to do first. I'm going to plug in a 0, some positives, some negatives. Let's start off by plugging in a 0. 2 to the 0 power, anything to the 0 power, is equal to 1. So when I plug in a 0, I get 1 as my output. When I plug 1 in for x, that's 2 to the first is going to be my output. 2 to the first, of course, is 2. So when I plug in a 1, that's 1 unit to the right, I get to go up 2 as my output. When I go 2 to the right, that's by plugging in a 2 for x. 2 squared would be my output, which of course is 4. And when I plug in 3, or go 3 to the right of the origin, I get to go up 2 cubed, which would be 1, 2, 3, 4, 5, 6, 7, 8. That's all that I'm going to be able to put, at least in that direction. 2 to the 4th would be 16, and that's off the graph patch, so I'm going to stop there. Now let's plug in 2 to the negative 1 power. If I plug in 2 to the negative 1 power, that's 1 over 2 to the positive 1 power. Negative exponents basically mean to take the reciprocal of my base. So when I go to the left 1 unit, I get to go up only 1/2. To the left 2 units, when x is negative 2, not only will I flip my base from 2 to 1 over 2, I have to square that to get 1/4. And then 1/8 and 1/16, and so on and so forth. And hopefully you believe me that there will be a horizontal asymptote right here, because we're actually never going to touch the x-axis. So I'll put that horizontal asymptote in there, and I will graph this curve right there. So that's our exponential curve if the base is 2. Remember, don't touch your asymptote, but the asymptote is nice to help the graph sit, well, into it nicely. I'm going to do g of x in blue. It's the same process, but a different base. Now I'm raising 4 to the 0, and 4 to the first, and 4 squared, and then to the negative powers. So let's plug in a 0 first. 4 to the 0, of course, is also 1, so they share that y-intercept. If I plug in a 1, 4 to the first power would be my output, so I'm going to be going up 4, 1, 2, 3, 4. So it's already a little bit higher than the red curve. And if I plug in a 2, 4 squared would be my output. 4 squared I can't really even fit on the graph patch, so I'm basically done. If I go to the left and talk about 4 to the negative 1 power, it's still a reciprocal idea, 1 over 4. Technically, that's underneath the red part of the curve. And then 1/16th and 1 over 64 and so on and so forth. Has the same horizontal asymptote. This time the blue is underneath the red right now until they intersect, and then the blue will be above the red, exponentially growing higher, faster. So those are the two f of x and g of x exponential curves. I'd like to talk a bit about all the little pieces for that function, for these functions. Let's first start off with the domain. Now, it doesn't matter which of these graphs we're looking at, they will both have the same answers. The domain, of course, is all reals for each one of these graphs. I get to plug in anything I want for x, and we actually just talked about that. X is an element of the real numbers. The range, though, goes from 0 to infinity for both of these graphs. In fact, we never touch the value of 0 in the range. We never touch the x-axis. So that's why I have a parenthesis here. Let's talk about the x-intercept. Actually, we don't have an x-intercept, so that's helpful to know. We don't touch the x-axis, so there are no x-intercepts. The y-intercept, though, is the same for both of them, and it's the ordered pair 0, 1. And that's helpful. I like to write it as an ordered pair to remind myself that the 0 exponent will create a 1 as an output. These are both increasing curves, and they are only increasing. They're increasing from the beginning of the curve all the way to the end of the curve. So since you only are increasing, that must mean that both of these are 1 to 1. Remember, a function is 1 to 1 if it passes the vertical line test and the horizontal line test. And that will tell us something about its inverse, but we'll be graphing those a little bit later. Vertical asymptote, we don't actually have a vertical asymptote, but the horizontal asymptote we do, which is y equals 0. It's the equation of the x-axis. So exponential curves have horizontal asymptotes. Let's talk about the end behavior. We do have two ends, and they're doing something differently on both ends. So let's talk about the far left end. As x is decreasing all the way down to negative infinity, you can see that both of the curves are trying to reach the value of the horizontal asymptote. F and g are both trying to approach 0. That's the far left end. The far right end, as x approaches positive infinity, let's see what's happening. As we increase the value of x up, 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 up the x-axis, I should say right, 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 the functions are skyrocketing all the way to infinity. So f and g are both trying to reach infinity. So let's look at our other two functions and see what happens when we take the base and do the reciprocal of 1/2. I'm going to do color coding again. I'm going to make h of x a red graph and do the same process. Let's plug in a 0. Anything to the 0 power, of course, is still a 1. When I plug 1/2 to the first power, then my output is only 1/2. And when I put x as a 2, 1/2 squared becomes 1/4. And you can see that my outputs start to decrease this way, which means that if I go to the left and do 1/2 to the negative 1 power, just like a negative exponent always does, it's going to take the reciprocal of the base. In this case, we're going to have an output of 2. And when I input a negative 2 or go 2 to the left, now I output a 4, because 1/2 will flip upside down and become a 2, and then 2 squared makes the 4. When I plug in -3 for the value of x, my output would now be an 8, 4, 5, 6, 7, 8, because it'll flip the 1/2 to a 2 and then cube it. Again, we still have that horizontal asymptote. We're not going to be touching the x-axis in this case. So I'll put that in there so the function can nicely rest on top of that almost. Well, of course, it doesn't touch it. And here is my reciprocal curve. Now we are decreasing. Let's do the same thing for k of x. I'll do that in blue. Anything to the 0 power, of course, is 1. When I input positive numbers, my fraction is going to get smaller. 1/4 to the first power, 1/4 squared, 1/4 cubed, become 1/4, 1/16, and 1/64. But when I input negatives, 1/4 to the -1 power, now our base is flipped and our outputs become 4 and 16 and 64. Of course, I'm not going to put those last couple because they're already too big. So there is our blue curve. Technically underneath the red curve over here and above the red curve over here to the left. Let's talk about the same stuff in the same order and see how things have changed. So our domain is still the same. It's still all reals. Our range is still the same. It's still 0 to infinity, everything above, all positives basically. Our x-intercept is the same because we don't have one, none. Our y-intercept is the same. It's still the ordered pair 0, 1. This time we are decreasing, but it's helpful to know that we are always decreasing. We do not decrease and then decrease like some polynomial function. We are always decreasing, which means that it will be 1 to 1. It passes horizontal and vertical, and therefore its inverse will be a function. Our vertical asymptote does not exist. Our horizontal asymptote, on the other hand, does, and it's y equals 0. And now let's talk about our end behavior. This time, if we talk about the far left end, as x approaches negative infinity, as we go down or left, 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 left on the x-axis, the function is skyrocketing to positive infinity. This is h and k are both trying to get up to infinity. Good luck, you can't touch that. This time on the right side, though, as we go right, 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 right up the x-axis, our value of the functions are decreasing, decreasing, decreasing to the value of 0. H and k are both trying to become 0. So let's look at one last thing. I'd like to look at what happens from 2 to the x and how that's comparable to 1/2 to the x. Obviously, they are different functions, but I'd like to know what happens so that we can graph these things by transformations. Well, if you understand, the 1/2 is coming from a negative exponent. So this is basically 2 to the -1 power raised to the x. That's what 1/2 is equal to. And 2 to the -1 raised to the x becomes 2 to the -x. So that's what happens here, and that is what's going to happen when we flip our graphs. If we have 2 to the x, and that looks like our basic red exponential curve, if we make the exponent negative, then we're basically flipping the base and making it look like this, and it's going to be the same curve but going in the opposite direction and becoming a decreasing curve. And it's important to note that that negative sign, when it's in front of the input, will reflect over the y-axis. If you took this red curve and imagined the y-axis as a mirror and flipped it or looked at the reflection in the mirror, you would have this red curve over here. And that's exactly what happens. When the input is negated, when the input has a negative sign, it is going to reflect, the values of the outputs will reflect over the y-axis. So this is a neat little concept to understand when we start doing our transformations, which is what we're going to do next. Let's look at our general form for our exponential curve. So f of x, let's put in a couple other parts. We could have a positive or a negative in front as a coefficient. A is going to be raised to the x minus h power, and then we're going to be adding the value of k. So what h will do and what k will do, it'll move our origin, our starting point. H, of course, moves horizontally, k moves vertically. We've seen graphing by transformations plenty of times. What I'd like to do is now let's change our base to be a base 3, and each one of these four functions you can see is using a base of 3. They're just transforming and going to different places, and let's see how we would graph that. So let's look at a of x. The first thing I'd like to find is what h and k are, because that'll tell me where my new starting point is. H is always up here in the exponent, and it's the number that would make the thing equal to 0. That's why it's always the opposite of this. So if I see x plus 1, h must be a negative 1. K is always the number that's being added or subtracted out here. Since I don't see it, it must be a 0. So negative 1, 0 is where I am. I go negative 1, 0, and put a little box or a little star or a little heart or some sort of indicator that that's where my new origin is. Once I have that, I know that I'm going to put a horizontal asymptote right on through it. I like to go a little bit below it so that I have some room for my points. That's it. Now the only thing I need to understand is that we're talking about base 3, and I'm talking about the special powers of 3. 3 to the 0 is 1, 3 to the first is 3, 3 squared is 9, and then 3 to the negative 1 is 1 over 3, and 3 to the negative 2 is 1 over 9. That's good enough. It's just my special powers of 3, starting from this new origin. So this new origin represents my 0 power. That's why 3 to the 0 power, I'm going to put a 1 right above that little box. Going to the right of that box, 1 unit to the right, is like the first power of 3, which would be 1, 2, 3. Back to the box. Going to the right 2 units is like putting 3 squared, and 3 squared, of course, is 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I believe you can do yours on your graph patch on your notes. I'm not going to go to 3 cubed because 27 is too large, but I will do this. I kind of call these the cheat points. I'm not going to whip out a ruler and make sure that you're actually going 1/3 and 1/9 or even 1/27th, but as long as they're there, then I won't be able to take off any credit. Just make sure that they're there. I want you to know, of course, that they're the numbers 1/3 and 1/9 and 1/27th. But there you go. So it's the basic exponential curve, y equals 3 to the x. It's just shifted 1 unit to the left because h was negative 1. Let's look at b of x. Same thing, I'd like to find hk first. H this time is just a 0 since I don't see anything added or subtracted to in my exponent. So h must be 0, and this number that's being subtracted now must be k. So 0, negative 2. This time 0, negative 2 would shift me down here, and I can put my little box there. Horizontal asymptote right through that box. Please put that as one of your first things. And now we just need to do the special powers of 3 from this box, from this new location. So this again represents my 0 power. The 0 power creates a 1, so 1 unit above. 1 unit to the right of my box, and I get to output a 3, 1, 2, 3, because that's what 3 to the first power is. And then go back to my starting point. 3 squared, I plug in a 2. 3 squared would be my output. 1, 2, 3, 4, 5, 6, 7, 8, 9. It's just 2 units off. I'll definitely put that one. And then the cheat points, 1/3, 1/9, 1/27th, 1 over 81 if you want to go crazy. And there we go. There's our exponential curve. Looking good. Let's see what happens with these two negative signs. I've got a negative sign in front of the entire function, and I've got a negative sign in d of x in front of the input of the function. Well, the negative in front of the entire function is simply going to flip you upside down. Flip upside down. That's what that negative will do. It'll take your normal 3 to the x function and flip it upside down. So it's actually going to be points below the horizontal asymptote. Everything else is going to be basically the same. H is 0, k is 0. So we're still starting at the origin, 0, 0. And we're still putting a horizontal asymptote, of course, right through that box or through that origin. But this time, what our outputs are going to be, instead of being above the x-axis, because those would be the positive ones, we have to multiply by, this is like a negative 1 times 3 to the x. All of our regular outputs are now negated, so we actually go below the box. 1 unit over, and instead of up 3, we go down 3. We go 2 over, instead of up 9, we go down 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'll just tuck it right in there. Instead of up 1/3, we go down 1/3. Up 1/9, instead we go down 1/9 and down 1/27. So that's what that negative sign is going to do. As opposed to this negative sign, which we just learned in the previous examples, this one flips in the y-axis. So wherever our points were going to be, we flip them over the y-axis, and that's where they will become. So h is still a 0 and k is still a 0, so I haven't done anything with that. Haven't done anything with our horizontal asymptote. But now let's see what happens. If we were going to graph y equals 3 to the x, it would look like this. I would have my 0, 1, and I'd go to the right 1 unit and up 3, and I'd go to the right 2 units and I'd go up 9. Let's say it's approximately right there. And then I do my cheat points 1/3, 1/9, and 1/27. What this negative sign does, it flips these in the y-axis. So obviously this one is already on the y-axis, so I'll just fill it in. This one will flip to the other side of the y-axis and be right here. This one will flip over the y-axis and be, well, it's kind of in my words here, so I'll just put it right in there. And these cheat points that were going to be down over here are now going to be on the other side. So that's what that negative sign will do. It'll flip your graph in the mirror of the y-axis. Or, if you'd rather understand that this negative exponent will flip that 3 to become 1/3, and you'd rather just graph this graph as 1/3 to the x, that's the same thing. You're going to be going to the left and then up, and going to the right and then, down these cheat points. So I don't know if it's helpful to make the note that this is flipping over there and this is flipping over here and so on and so forth. That might be helpful. So we'll explore these transformations in class. Make sure you bring some graph paper. I do want to show you one last graph in this tutorial, and that involves the number e. E is probably our second most famous irrational number. E occurs in many natural patterns, in many patterns in nature. And we're actually going to look at some of the applications of E later on in this unit. It occurs in many patterns in nature. That's why it's the base of the natural log system. We'll find out in nature. If I could spell, that would be great. E is, first of all, it's above the division button on our calculator. So if you're looking for it, it's right there on our calculator, at least on the TI. And E is approximately 2.7182881828459045. That's all that I've remembered. Sorry. It does go on forever because it is irrational. It's just another number. It just happens to not be a nice integer base. It's about 2.7. Okay. E squared we might need. So just so you know, E squared is approximately 7.4. And E cubed, you'd think we might need, but that's about 20 point something. So I'm not even going to worry about that because we're very rarely going to be counting 20 tick marks. Though I do believe it's about 20.1. Just because I like to have correct stuff there. Okay, so if we were going to graph example 3, g of x equals negative e to the x minus 3, let's go ahead and graph this. First, let's find our hk again. H in this case is 3, so 3 units to the right, and k is 0. There's nothing added over there. So I'm going to go 1, 2, 3 units to the right and put a little box, and I'm going to put my horizontal asymptote right on through that box. There we go. And now there's one other thing, well, two other things I need to worry about. I do have this negative sign. Now that's the negative sign in front of the entire function. So that's going to flip upside down. So we're actually going to have the values be below the horizontal asymptote. And the other thing I need to worry about is that we are talking about base e, so I need these numbers, 2.7 and 7.4. Of course, e to the 0 power, anything to the 0 power, is going to be 1. But instead of going up 1, because of that negative, it's going to force me to go down 1 unit. Now when I go to the right one, normally I'd be going up, but this time I'm going down. And I'm going down e units, which is about 2.7. So 1, 2.7, approximately right in there. And then back to the starting point. Now when I do e squared, I'm going to go down about 7.4. 1, 2, 3, 4, 5, 6, 7, 0.4, something like that. Cool. Now our cheat points would be down 1 over e, whatever that is, and down 1 over e squared, and down 1 over e cubed, so on and so forth. So the points are getting closer and closer and closer to the horizontal asymptote, and there is our function. Flips upside down because it's a negative function right there. Let's just review our domain, range, horizontal asymptote, and y-intercept. Our domain, of course, is still all reals. I can plug in anything I want for x. This time our range has kind of flipped upside down. We start at negative infinity, and we get all the way up to 0. We don't include the 0. A horizontal asymptote is still, in this case, y equals 0, the equation of the x-axis. And our y-intercept, I see where it crosses the y-axis, but what is that number? Well, if you remember, this was, down 1. So this is down 1 over e. This is down 1 over e squared, and this is down 1 over e cubed. So this is negative 1 over e cubed. I probably need my calculator to plug that in and see approximately what that is equal to. And that is approximately negative 0.0497. You can also, of course, find any y-intercept by plugging a 0 in for the value of x, so we get negative e to the negative 3. The negative 3 power, of course, flips it upside down to become 1 over e to the positive 3 power. So we got some practice to do with our graphs. I'll see you in class. Thanks a lot. Bye.